All right, welcome. So in this video, we will discuss some arithmetic that we can do with vectors. So the first operation I want to talk about is addition. So how do we add two vectors, and what is kind of the geometric significance of the sum of two vectors? So let's imagine we have two vectors u and v that are in Rn. Then the way that we add these two vectors together is we add all of the components. So I take the sum of the two first components. That's going to be the first component in the sum. The sum of the second two components will be the second entry in their sum. So for example, here we have a couple of examples, and if you're writing these out, again, it's hard to write in boldface, so I might encourage you to just use the arrow notation instead. So if I want to write the sum of u plus v, then I would just add the components. So I'm going to take the 2 plus the minus 6, and I'm going to take the 2 plus the 2. So I just add these two components. I add the 2 and the minus 6, I add the 2 and the 2, and out comes a vector minus 4, 4. So that would be the sum of those two vectors, and that's it. Same idea over here. If we wanted to add u and v, now we do the same exact thing, just we have four components to be mindful of. So I would take the 1 plus the 8, the minus 3 plus the 2, the 8 minus the 1, and the 0 plus 3. And adding this together, then doing the arithmetic, we would get 1 plus 8 is 9. That's a minus 1. This is 7, and then we have a 3. So the sum of these two vectors would result in something in R4, where the first entry is 9, minus 1, 7, and then 3. Okay, so hopefully the mechanics of doing this, it's just doing several addition problems. But a couple of observations that are really important to point out, and that is we can only add two vectors if they have the same dimensions. So for example, I couldn't add this vector u to 2 with this vector v because this has 2 dimensions and this has 4 dimensions. So we can only add two vectors if they have the same dimensions. If they do not have the same dimension, then their sum is not defined. And secondly, when we add two vectors, the result is another vector, and that vector is going to have the same dimensions as the two vectors that we added together. Okay, the next operation on vectors that I want to talk about is how can we multiply what's called a scalar times a vector. So we'll see multiplication with vectors is a little bit more complicated. There actually are different ways that we can define the multiplication of two different vectors. That's not what we're going to do here. So first of all, what I mean by a scalar, so quantity that only has magnitude and does not have any direction, that's a scalar. And in other words, these are just numbers that we're typically used to working with. So things like minus 4, square root of 5, 0, e squared, these are all numbers. They have a magnitude, but they do not have a direction. So let's first talk about how we can multiply a number and a vector. So given any vector v, in this case, which is in Rn, that I'm denoting with this bold v, and a scalar, which we denote unbolded without an arrow above it. So this scalar is a c. And so now hopefully you start to see the importance of keeping the notation separate for vectors and scalars, because these are different objects and the way that we do arithmetic with them is different. So I've got a vector v and a scalar c. We define the scalar product of c, scalar c, and vector v. We write that just as we typically write products, cv. But what we do here is we're going to multiply every single element of this vector by this scalar c. So we just multiply the first one by c, the second one, and so on. So again, this is also hopefully a pretty intuitive way that you might think about defining this product. So let's take a look at a couple of examples. So let's say I have a scalar c, which is minus 3, and a vector v, which is 2 minus 5. Then what would the product of these two vectors look like? I would take c times the vector v, and so I'm going to say minus 3 times 2 minus 3 times minus 5. So I just multiply each of the two components of the original vector v. Each of them I'm going to multiply by minus 3. So I get a minus 6 and then a positive 15. So I would say that C, the product of C and V, gives me a vector minus 6, 15. And jumping up dimensions doesn't change how we're going to define this operation. It just means we have to do a few more of them. But if I have a vector in 3 dimensions, then I'm just going to take this 2 and multiply it by the first entry. I'm going to take this 2 and multiply it by the second entry. And I take this 2 and multiply it by the third entry. And then that result is the product of C and V. So here we can multiply any scalar times any vector. So this is defined no matter how many dimensions V has. So this is going to be a well-defined operation no matter what we have for V and C. However, what's important to note here is that the result is going to be a vector that has the same dimension as the original vector. So we started with a 2-dimensional vector, we wind up with a 2-dimensional vector. We start with a 3-dimensional vector, then the scalar product is going to be a 3-dimensional vector. So on the next slide, I want to take a look at how we could imagine these operations visually.